Have you ever just stopped and wondered about what's going on inside your own head? I mean, every single second, your brain is pulling off these computational miracles that just feel, well, effortless. But what's the actual architecture behind it all? What's the mind's blueprint? Let's dig in. Seriously, think about it for a second. How do you go from not knowing something to knowing it? What is it that actually physically changes inside your brain? Or, okay, how about this? When you're faced with a simple decision, what's the internal process? What's happening in there that tips the scales from one option to another?
And maybe the most fundamental question of all, how do the patterns of light hitting your eyes turn into the rich, three-dimensional world that you're experiencing right now?
Now, this might sound a little strange, but all of these deeply human experiences, seeing, learning, deciding, they can actually be described with the precision and, really, the elegance of mathematics. Today, we're going to explore that blueprint, the hidden math of the mind. All right, let's start at the very beginning, perception. How does all that raw data from our senses become something meaningful? Well, it all starts with the code that our neurons use to talk to each other. You know, for the longest time, the big debate in neuroscience was basically this. Is information all about how often a neuron fires? Or is it about the precise timing of those signals? The classic view was all about the firing rate, but a newer idea suggests that timing is everything. And this leads us to this really cool principle called spatiotemporal coding. So it's not just a simple on or off signal. The brain's language is much more like a complex piece of music. The meaning comes from which notes get played, sure, but also in what order and with what kind of rhythm. So how does this actually work? Well, think of a neuron like a really picky bouncer at a club, a coincidence detector. A signal coming from neuron A is like one person showing up at the door. A signal from neuron B is another person. Now that bouncer, our target neuron, is only going to open the rope if they arrive at almost the exact same time. That's how the brain recognizes patterns. It detects when specific signals arrive together. Okay, so our brains can see the world, but how do they actually learn from it? How do we turn an experience into knowledge? Well, that brings us to the mathematics of learning. The old school way of thinking about memory was kind of like a filing cabinet. You know, you have an experience, you write it down on a card, and you file it away. But mathematical psychology helps us see it in a totally different way, as a living, dynamic network where the connections themselves are the memory. And it all hangs on this one crucial principle, first thought up by Donald Hebb way back in 1949. It's so simple, but it's incredibly powerful. You've probably heard the saying, neurons that fire together, wire together. That's it. That's the fundamental rule for how our brains physically change when we experience something. Let's just watch how this plays out. So here we've got two neurons. Let's say one represents the smell of coffee and the other one represents the image of your favorite mug. Right now, they're not really connected. They're not talking to each other. But then you have your morning coffee. The smell neuron fires, and at the exact same time, the mug neuron fires. That experience links them together. And because they fired together, the physical connection between them gets stronger. A pathway gets built. Now, just smelling coffee might be enough to make you think of that mug. That strengthened connection, that is the memory. So if learning is all about strengthening these connections, you can start to imagine all of our knowledge as this huge interconnected map. And mathematicians actually model this with things called knowledge spaces. They can literally create a structured map of what you know and then show you the most logical path to what you're ready to learn next. It's kind of like a personalized GPS for education. So we can see and we can learn. But what about actually doing things? How do we make a choice? Well, it turns out there's a calculus for that too. Let's just take a simple everyday decision, coffee or tea. It feels instantaneous, right? But underneath the surface, there's a fascinating mathematical race happening. One of the leading models for this is called the diffusion decision model. And the best way to think of it is like a mental race. Your brain starts collecting little bits of evidence for each option. You know, memories of how coffee tastes, what time it is, how tired you feel. It all starts adding up. And the race is on. The evidence starts to pile up. Your memory of that amazing espresso you had this morning gives coffee a bit of a head start. It's pulling ahead, but the race isn't over yet. And there it is. The evidence for coffee hits a critical decision threshold. The race is won. The decision is made. What's amazing is that this model can predict not just what you'll choose, but with incredible accuracy, how long it'll take you to choose it. So, We've peeked at the math behind seeing, learning, and choosing. But why does mapping out this blueprint of the mind matter so much? What's the point?
Okay, let's just pull it all together. What have we seen? We've seen that perception is a code that's all about timing. Learning is a physical process of strengthening connections, and making a choice is basically a race to accumulate evidence. The common thread here? All of these deeply human mental processes, they follow predictable mathematical rules.
And this, right here, is the crucial takeaway. By understanding the mathematical rules that our own minds run on, we get the exact blueprint we need to build intelligent machines. The neural networks that power so much of today's AI, they are the direct descendants of these very models of the human brain. And that brings us to a final, really profound question. As we keep decoding this mathematical blueprint, we're not just understanding ourselves better, we're literally writing the instruction manual for creating a new kind of intelligence. So if we can actually write the entire blueprint, does that mean that one day we could build a mind from scratch? That's something to think about.